We're now ready to look at the three different types of terms that would be involved in a transfer function's numerator or denominator. The first term is a constant term k. The second term is a simple real root, I should say, s plus a, or as we'll see, we'll write it as s or a times s over a plus 1. So this is a simple real root. Okay, this is a constant. It's real valued. That's because we are dealing with real systems. The third term is a s squared plus bs plus c, so it's a complex conjugate root pair. So that's what we're going to be developing now. How do we plot each of these? So case 1 for constant k. I'm going to increase my pen size. The magnitude of a constant k is just going to be equal to absolute value of k. All right? And the angle of k is going to just be equal to 0 degrees if k is positive, and 180 degrees if k is negative. All right? So if our transfer function were something as simple as minus 10, all right, that would say that whatever this system is, it has a gain of it amplifies whatever comes in by a factor of 10, but it flips the sign. So if we were to plot the magnitude and phase versus frequency, we would say that the magnitude of g is at 10, and we would say that the phase is at either at plus 180, or we could say minus 180. Either way would work. Let me break this. Okay, plus or minus 180, that wouldn't matter. So this is the angle of g. That would be our Bode plot for such a simple system. The point is that if you have a negative sign in your transfer function, it's never going to show up as being negative magnitude. Right? In fact, I should redraw this on a dB scale. This would be 20 dB. Right? And if, for example, okay, if g of s were equal to 0.1, okay, now the magnitude plot would look like this. Versus omega, we would have, again, it's a constant magnitude, but what would this value be? It would be minus 20 dB. Remember, we have 20 decibels per decade when we're talking about field quantities like voltage or force or temperature. And so we're a factor of 10 less than 1, so we're 20 dB down from our reference level of 1. That was our simplest case. Secondly, let's consider our s plus a term. We're going to rewrite this. This is a preference, but I think it's a good convention. We're going to write it as in a normalized form. So this here is a normalized form, and you'll see why in a moment. Okay, so let's first consider s plus a. So if we have, let's say that g of j omega is equal to s plus, or j omega plus a, what is the magnitude of this? Well, the magnitude, and I'm going to be short about this, I should write g of j omega, but I'm leaving it off, it's implied here from the context, is going to be the magnitude of j omega plus a, which is, what are we doing? We're looking at real axis and imaginary axis, and we have this vector here that has a real component of A and an imaginary component of j omega, and so it has a magnitude m, has some angle theta, and so the magnitude is going to be the square root of the sum of the squares, right? And this is equal to m. Now we can make some approximation. This is where this technique becomes powerful, because calculating the square root of a squared plus the omega squared is not something you want to do in your head. However, we can look at its asymptotic values. So for instance, when omega is much, much less than a, okay, so at least an order of magnitude less than a, then we would say that the magnitude would approach just a, right? Square root of a squared plus something very small squared. When omega is much, much greater than a, now omega squared dominates the a squared, and we would say that the magnitude approximates omega. And let's look at the special case where they're equal to each other. Here we would have a squared plus a squared. So we have a times root of 2. Now let's consider the normalized case. If g of s is equal to s over a plus 1, right? Then we would write the magnitude of g of j omega is equal to magnitude of j omega over a plus 1. And here we could write the same three cases. When omega is much, much less than 1, now we have essentially just the real part, which has a value of 1. We have when omega is much, much greater than a, then we have the imaginary part that dominates, so we have an omega over a. And when omega is equal to a, we have j plus 1. So we have square root of 1 squared plus 1 squared, or square root of 2. Now if we plot this, let's look at the decimal value before we plot it. The decimal value of g of j omega is going to be equal to, or we'll say approximately here. It's approximately going to be 0 dB for omega much, much less than a. It's going to be, I didn't mention this in the last video, but the square root of 2, 20 log square root of 2, is approximately 3 decibels. Okay, this is when omega is equal to a. And when it's much, much greater than a, then we'd have 20 times the log of omega over a. Okay, but we can rewrite that as 20 times the log of omega minus 20 times the log of a. So this is an offset, all right? But this right here determines the slope. Okay, in fact, this right here is the slope if we plot the decibel of gj omega. Okay, we plot it versus not omega, but let's say we plot it versus the log of omega. Then we would have this. Let's draw a on here. Okay, and we have much less than the log of a, we would have something that's flat and at 0 dB. And then when we're much greater than A, we have this slope of minus 20. So we'll have, oh, actually we have plus, I'm sorry. In this case it's plus. Okay, this has a slope of 20 dB per decade, right? A decade of frequency. And what we can do is, instead of writing, if we do log of omega, then we'd plot things like 1, 2, 3, or maybe we'll start here, we'll do 1, 2, 3, 0, minus 1, right? Where this would be, if I actually, so this is log of omega, and then omega here would be the anti-log of that. So this would be 1 radian per second. This would be 10. This would be 100. This would be 1,000. This would be 0.1. So what we typically do is we don't actually plot on the horizontal axis the log of omega, but we'll just put the radian frequency or the Hertz cycle frequency, but we'll at equal spacings we'll put powers of frequency. So we'll do something like this. Let me redraw this. And we'll say 1, 10, 100, 1,000, or 1K, and 0.1, and so forth. And we'll just label that omega. But by the scaling of the axis, it's clear that we're plotting this versus log. It's on a log scale, right? And then on the horizontal, on the vertical, we'll do things like 0 decibel, minus 20 dB, plus 20, and so forth. So if we were plotting g of omega, magnitude of g of omega, where g of omega is equal to this j omega over a plus 1. Okay, and let's assume, let's let a in this case equal 10. Okay, 10 radians per second. Then we say at far below a, which is far below 10, the magnitude we saw was 0 dB. And I'll draw a dotted line here. And above, far above omega, or a, it's going to have a slope of 20 dB per decade. So here is 1 decade, and here is 1 decade. All right, so I'm starting from my corner frequency, and I'm going up. Let me redo that. Now the reason I do that dotted right around this corner frequency is because the actual magnitude at omega equal 10, right? If we look at we saw that the magnitude at omega equal a is square root of 2. Right? And just to be explicit, we have j omega over 10 plus 1. We're saying, what is the magnitude of that when omega is equal to 10? Well, it's equal to magnitude of j plus 1, which is square root of 1 squared plus 1 squared, or root of 2. And the decibel value of root of 2 is approximately 3 dB. So we know that actually, okay, so at omega equal 10, we're at 3 dB, which is about here. I mean, that's 4. Right around there. Okay, so this would be 3 dB. So the actual response is going to go through that line. And I'll just kind of fill it in. So the regions that I'm confident in are this asymptotic value for slope down here, and the asymptotic slope up here. This has a slope of +1. This has a slope of 0. Right? And then I know this singular point right here. And by knowing the high and low frequency asymptotic slopes, and by knowing the corner frequency, or the frequency of this 0, I can now plot the magnitude. Now let's consider the case of a little different transfer function. G of j omega is equal to 1 over j omega over a plus 1. Okay, so this would just be the g of s is equal to 1 over s over a plus 1. All right, so I flipped this simple root, I put it down in the denominator instead of the numerator. Well, the magnitude of g is equal to the magnitude of the numerator divided by the magnitude of the denominator. And if I plot this in decibels, magnitude of, let's put it this way, g in decibels is going to be equal to n in decibels, remember, minus the denominator in decibels. So I already determined what the magnitude plot looks like of a j omega over a plus 1 term looks like. That's this guy right here. All right? And now this new transfer function is simply has a magnitude that's opposite in sign to that. So we can very easily plot this as omega, say 0.1, 1, 10, 100, whoops, and 1k, we'll say 0 dB minus 20 dB minus 40 dB. And my corner frequency is again right at omega 10. And I have my asymptotic line here, 0 dB. Minus 0 dB is the same as 0 dB. But now instead of having a rising slope, I'm going to have a falling slope. That'll look like this. And once again, I'm going to, at the corner frequency, I will be 3 dB off, except in this case, I'm going to be 3 dB down. So the actual curve would look something more like this. This is the magnitude of g of j omega, which is equal to 1 over 1 plus j omega over 10. That's what we just plotted. Now let's look at the angle. So if we go back to return to g of s equal to s over a plus 1. Right. The angle of g of j omega is going to be equal to, remember, the angle of the numerator minus angle of the denominator. I have no denominator here. The denominator is 1, right? So it's simply the angle of j omega over a plus 1. And this is simply the arctan of the imaginary part. Right? We have 1, and here we have omega over a on the imaginary axis. Right? And we're looking for this angle here. So it's arctan of omega over a divided by 1. Right? It's just arctan of omega over a. And let's see, go back if we talked about this yet. No, we did not. We did not talk about the angle. So we can approximate this. Angle of j omega over a plus 1 is approximately equal to, now when omega is much, much less than a, then we have essentially the arctan of 0. And this line here is laying down on the horizontal axis. So we have an angle of 0. And when omega is much, much greater than a, we have essentially the vector here is pointing straight vertically up. So we have 90 degrees. And when omega is equal to omega a, we have the arctan of 1. Right? Arctan of 1, which is going to be equal to 45 degrees. So we're halfway in between. Now another thing to note is the arctan of 10 is equal to, I better pull it up here just to be sure. Arctan of 10, where's my 10? Okay, is 84.3 degrees. Arctan of 1 is 45 degrees. Arctan of 0.1, oops, no, 0.1 arc, is 5.7 degrees. So if we plot, let's plot the phase versus omega, but we're going to use the log scale again. So we'll have 0.1, let's start at 0.01, 0.1, 1, 10, 100, and 1,000. Now we can start at, and let's assume A is equal to 10. So we're plotting the angle of j omega over 10 plus 1. So we can, the easiest one to evaluate is when we're right at that that pole frequency, or that zero frequency, which is 10. So j omega, j10 over 10 plus 1, that's angle of j plus 1, that's 45 degrees. So we'll position that right here. We'll say this is 45 degrees. Then, based on these calculations, we see that if we're a decade below, in other words, down here, we are at about 5.7 degrees. Okay, I'll just put a dot here. This is 0 degrees. And we'll say up here we're at 90 degrees. And a decade above, we're at 84 degrees, which puts us very nearly there. We can now, well, I mean, the actual curve is going to look like something like this, right? But we're going to do a straight line approximation by pinning the phase right at 45 degrees when we're at the corner frequency, and we're going to assume that, or claim that, essentially the phase finishes transitioning when it's a decade above and a decade below that frequency. So we're going to draw something that's going to intercept here, it's going to intercept here. We'll draw a straight line here, and then we'll draw a straight line beyond that. Okay? So this is decade below. This is decade above. So we allow 2 decades for phase to transition from, or based to transition 90 degrees. This would be the same if we were going from 90 to 0, if we were going from 0 to minus 90. If we're doing a transition of 90 degrees, we're going to allow 2 decades, where 1 decade above the corner frequency, 1 decade below, and right at the corner frequency, or that root frequency, will be halfway between the transition. So that's how we construct a phase plot. Let's now return to the second transfer function we had considered. Okay, g of omega is equal to 1 over, let's just write g of s first. G of s is equal to 1 over s over a plus 1. Let's write it as 1 over s over 10 plus 1. And we can write this, the form you might find the transfer function in initially is something closer to 10 over s plus 10, right? But I always like having a term in s plus 1, and then it's normalized. What that tells me is that when the s goes away, if I'm going to very low j omega, then that particular term, this s over 10 plus 1, will asymptotically go to 0 dB because it'll go to a gain of 1. So that's the reason that I like normalizing. So even if I'm giving something like this, I will normalize it. What if I'm given something of the form 3, say 1 over s plus 10? Well, I still would go about dividing through by 10, and I would have 1/10 over s over 10 plus 1. I would divide by 10 because I want to get rid of the 10 there. So now this, I have two terms. I have 1/10 times 1 over s plus 10. Now when I plot the magnitude in order to plot the magnitude response of G1, the overall transfer function, I will plot the magnitude of 1 over s over 10 plus 1, which we've already done, and then the whole thing gets scaled by 1/10. Well, in the decibel scale, 1/10 is minus 20 dB, so all I have to do is to shift my curve down by 20 dB. Okay, and of course 1/10 does not affect the phase. Let's do the magnitude and the phase plot of our g of s here. So we have magnitude of g of omega, g of j omega, is equal to 1 divided by magnitude of j omega over 10 plus 1, right? And we already computed this, so let's just go ahead and draw this. Say omega, we'll have 10, 1, 0.1, 100, 1k. Okay, and then say this is 0 dB here. This is minus 20 dB, minus 40 dB. And so we put our breakpoint right here. Straight line approximation would be flat up to 10, and then we're going to decrease by a slope of minus 20 dB per decade from there on out. Of course, we're down at 3 dB below that, but we don't always even bother to draw that. It's understood that if you see this kind of plot, no one's claiming that the gain, the magnitude gain at omega equal to 10 is 0 dB. Someone knowledgeable about Bode plots would realize that the actual gain at omega equal to 10 is 3 dB down from that breakpoint. Okay, so that's the magnitude. And then now let's add in the phase. The phase we drew previously, but I'm going to draw the phase on the right side here. And let's start at, we'll say this is 0 degrees. This is minus 45 degrees. And down here this is minus 90 degrees. This is plus 45 degrees. Okay, we saw that at the breakpoint. At the breakpoint, the phase of our, we could say this is equal to Now, the angle of j omega is going to, g of j omega is equal to the angle of the numerator, which is 0, minus the angle of the denominator. Right? And we plotted the angle of the denominator previously, right here. Now that that term is down in the denominator, we're going to put a minus sign in front of it. So we're beginning at a phase of 0 when we're at very low frequency. Okay, so that's this guy here. And asymptotically, we're going to minus 90 down here. At the breakpoint, we're halfway there, and then remember we span a decade above, a below, and a decade above. So we say the transition will take 2 decades, like so. So this here is angle of g of j omega. So how do we interpret this? Let's suppose exciting the system at 100 radians per second. So I'm going to excite the system with cosine 100 radians per second. I drive my system g of s with that, and I get some output. And I'm told here that the output is going to have a magnitude of, I looked this up here, the magnitude at this point is minus 20 dB. So it's going to be minus 20 dB is 0.1, right? 0.1, this is just antilog of minus 20 dB over 20, right? Times cosine of 100t plus whatever my phase is. Well, my phase at this point is minus 90 degrees. If instead, let's say that I was exciting it at this frequency right here. What is this frequency? If you're halfway on a decade scale, you'd be approximately 30. Okay, so approximately 30 radians per second. So if I drove this with cosine of 30t, the response here, I'm told I would be minus 10 dB. Okay, minus 10 dB, 1 over the square root of 10. Okay, since minus 20 dB is 0.1. All right, so it's really like, or you can look at it as square root of 0.1 times cosine of 30 times, and now what's my phase? The phase is, it looks like it's between 45 and 90, so that would be 67, minus 67 and a half. Let's say minus 67, this is all approximate. Okay, so the frequency response plot is very useful to understand the dynamics of the system, how it will process different sinusoidal or spectral components of a signal. And remember, in this case, we've constructed this graph completely by hand. We didn't use a computer to do it. And in the process, we probably understand something more about the system than we would otherwise, because we've had to put some thought into it. We've had to not only consider what roots does it have in the numerator or the denominator, but where are they located, which ones that are higher frequency, which ones that are lower frequency. In this case, of course, it's simpler because we have just one pole. Okay, now we'll do another example where we use just simple roots, and then we'll look at the second order term after that. So let's consider a little more complicated g of s. We'll have s, say 1 over s plus 1 times s plus 10. All right. How would we do that? Now you might have been given the form, might even be given something like this, s squared plus 11s plus 10, right? In which case you'd want to factor it. Now I want to normalize this. I see a 10 here. I want to have a term of 1. So I'm going to divide through by 10 on the top and bottom. So I'll have a 1/10 s plus 1 and an s over 10 plus 1. I'm going to rewrite this as d1 term over n1 term times n2. Oops, did that backwards. n1 over d1 times d2 term. And in fact, we will use different colors. We'll use blue here, we'll use green, and we will use red. And we're going to plot, let's do the magnitude first, okay? Let's put our axes down. What you look at is you look at where are the break frequencies here. We have something at 1, right? Or let's actually write this more explicitly. We have S over 1. So I have 1 and I have 10. Okay, so if you're looking at how do I scale my omega axis, where should I put my limits? Well, things are happening around 1 and around 10. So let's make sure that those fit right in the middle of our graph plot and that we can go at least a decade, if not 2 decades below and above that. So let me start at 0.01, 2 decades below. And then I want to go up to 100 or K. So I want to go 5 decades here. So we'll say 0.1, 1, 10, 100, and 1 kiloradians per second. Okay? And what we're going to do is we're going to plot each one of these terms separately, and then we're going to combine them together. So let's look at term N1. Let's do the magnitude plot of N1. It's the magnitude of 1/10, or 0.1. And that is nothing more than minus 20 dB. So I'm going to set this at minus 20 dB. And we just have a line here. This is magnitude of N1. Right? Then we have the term D1, and that is S over 1 plus 1. And so we have at omega equal to 1, it would be our break point. And let's see here, we'll say this is 0 dB. This is 20 dB. So we'll set our break point here. And for frequencies much less than 1, our term D1 has a magnitude dominated by the real part, which is 1. Right? And then above that, we're going to increase at 20 dB per decade. This is the magnitude of the D1 term. Now, if I plot really the 1 over D1, then I would have the opposite of this. I would have this right here. Right? This is magnitude of 1 over D1. Actually, that's going to be more useful, of plus 1 minus 1. Right? Now let's plot the third term. The third term has a break frequency at 10. It also has an asymptotic gain of 0 dB below that. So we'll draw this superimposed on here. And then it's going to go up as well by the same amount as D1. All right. Magnitude of D2. And we can do the same thing for the 1 over D2 term. Right? Oops, this is slope of minus 1. Okay, that looks a little confusing, but the beauty of plotting this on a decibel scale is that now the overall transfer function magnitude is simply the addition of all 3 of those terms. What 3 terms? Well, we have this piece here, we have this as our second term, and we have this as our third term. Now we could do 1 plus 2 plus 3, or if call this 2 prime and call this 3 prime. So we could say the magnitude of G is equal to the magnitude of 1 plus the magnitude of 2 plus the magnitude of 3, or we could also write it as the magnitude of 1 minus the magnitude of 2 prime minus the magnitude of 3 prime. I prefer, since we've already drawn the 1 over D1 and 1 over D2 magnitudes, let's just add those together. So we'll do 1 plus 2 plus 3. How do we do this graphically? We start try to find a place on the graph where if everything is flat, it won't always be the case, but here, in this case, down at low frequencies, over here on the 0.01, 0.1 axis, everything has a slope of 0. So now we just add these up. I have minus 20 dB, I have 0 dB, and I have 0 dB. Add those all together, and we end up with minus 20 dB. So I'm going to have minus 20 dB down in this region. And I'll have minus 20 dB all the way up until I reach a breakpoint, which is right at 1 radian per second. At that point, the slope, number 2 here, starts rolling off. Here, this dotted green line that has a slope of minus 1. And so the other two, the red and the blue, continue to have a slope of 0. So they're not changing. But the overall now is going to track with the dotted green line. Okay, and I should put this is going to be minus 40 dB. Okay, and then I stop at 10 because there's something else that happens at 10. We have the breakpoint for D2, 1 over D2. And at that point, now I have 2 of my 3 terms. My second and my third terms both are rolling off at a slope of minus 1. So when I add those two together, I end up with a signal that drops off at 2 orders of magnitude per order of magnitude of frequency. So I have minus 60 dB here, and let me just see if I can fit this on here, minus 80 dB down here, okay? What this tells me is that if in the next decade of frequency, between 10 and 100, I'm not going to drop by a decade in magnitude, I'm going to drop by 2 decades, which means I will be down 40 dB. Okay, so this has a breakpoint, this is a slope of minus 1, and then oftentimes we'll actually label the slopes in case our drawing is not too clean or clear. And then we keep going up in frequency and we look, does anything else change? Like for instance up here, are there any more breakpoints above this? And the answer is no. The term 1 always has a gain of minus 20 dB. The red continues to go down at, the green continues to go down at minus 20 dB per decade. The blue continues to go down, the red continues to decrease at minus 20 dB per decade. So this slope here is our high frequency asymptote. The asymptotic values don't always have to have a constant value. They actually have a constant slope. So they could settle out at a slope of 0, in which case the value itself, the magnitude, would be constant, but it could also settle out at a constant slope. In this case, the asymptotic slope is minus 2 decade per decade, or minus 40 dB per decade. What does this mean? It means that for every decade of frequency increase, the gain, or the magnitude, of our transfer function decreases by 2 orders of magnitude. So there is the signal that gets through, the 100 radian per second signal that appears at the output will be 100 times smaller than a same magnitude 10 radian per second signal that is applied at the input. So this is a low-pass filter. You can see this from the overall magnitude curve here. And it's actually a second-order low-pass filter, because first-order low-pass filter would have just continued at the minus 1 right here. Okay, that's the familiar first-order RC filter that you've been working with. But we could add in some more circuitry, another capacitor, some more resistors, or another resistor, and we could have a second-order filter where now it more aggressively filters higher frequencies. And oftentimes that's a desirable thing. Now we haven't drawn the phase yet that we need to tackle next. Let's just extend this. Now I'm going to just by looking at this, I can tell that because the ultimate asymptote for this transfer function is negative, and it's -2, I think I mentioned early on that you will asymptotically incur 90 degrees of phase for every degree of slope. So if you have a slope of +1, such as here, you would incur asymptotically plus 90 degrees. If you had a slope of -1, like here, asymptotically you will incur minus 90 degrees. So asymptotically, the overall transfer function has a slope of -2. That tells me that asymptotically, the phase of the transfer function at high frequency will settle out at -2 times 90, so -180. So I'm going to scale this with that in mind. So I'm going to put 180 minus 180 down here. And then when I look at asymptotic low frequency value, there's a slope of 0. If the slope of the magnitude is 0, the phase that corresponds to that is 0. Right? I mean, I could have a sign reversal, and that could add or subtract 180. But in this case, I look at my transfer function. I don't have a minus 1/10 here, so it's positive. So I know that my low frequency phase is going to be 0. So okay, we'll just say 0 and minus 90 here. All right. Once again, we can plot the contribution from each of the terms. So we'll start with the blue, because that's the constant term. 1/10, it has a phase of 0. Okay. Term 2, D2 here, has a breakpoint at, I'm sorry, the green has a breakpoint at 1 radian per second. Right? And it's breaking from 0 slope to +1 slope. So let's put 90 degrees here. So it starts at low frequency, it'll start at 0 degrees. And remember, it's halfway through its transition at the corner frequency. So at 1, it'll be at 45 degrees. And it begins a decade below and settles out a decade above, by 10 in this case. All right, so this is angle of D1. And finally, the second term is going to be this, or the angle of D2 is going to be the same, but its breakpoint is at 10, so we'll be at 45 degrees at 10. It starts transitioning a decade below, and it finishes its transition a decade above. And now we have to put these three together. Now, look, in a similar fashion as with the magnitude, since D1 and D2 are in our denominator terms, I can plot. Let's see here. I can plot the angle of 1 over D1 or D2 this way. Okay, and similarly, D1 here, angle of 1 over D1. Okay, so now I'm simply going to add the three together like I did before. I'm going to add this term, I'm going to add this term, oops, and we're going to add this term, and we will have our overall phase. So we begin again at the low frequency where everything is not changing. We start at 0, all right? And the first thing that happens is the green breaks. We're going to follow that line. We follow that line up until about 1 radian per second. Why? Because at 1 radian per second is a decade below where D2 has its breakpoint. It's at 10 radian per second. And so its phase is beginning to transition. At this point, we now have two transitions in phase. The green is still dropping at the same rate, but the red is dropping at the same rate as the green, and so it doubles. So we will go and that'll happen all the way up to 10 radians per second. So we will have an increased slope here. And now we can check, where does this end? Well, at this point it should end with, we have a contribution of minus 9 degrees from the green, and we have minus 45 degrees from the red. So we have a total of minus 135. Minus 135. At that point, the green flattens out and no longer contributes any additional phase. The red is still transitioning. It still has another 45 degrees to go. Where does it end up? Well, down at this point here, by the time we get to 100 radians per second, we have minus 90 degrees from the green, minus 90 degrees from the red, and 0 from the blue. That gives us a total of minus 180. So this is where it'll bottom out, but it transitions like that. And that's not very clear. Let me just draw this down here to exaggerate this, okay? It's kind of like it transitions like this, then at twice the slope, and then at half the slope again, all right? So there we have it. This here is the overall angle of our transfer function. At low frequencies, it has no angle, 0 degrees angle, which makes sense if this is a low-pass filter. For low frequencies, we're not affecting anything that comes through. We pass it right on without attenuating it, without phase shifting it. And if we go to very high frequencies, the attenuation is 2 decades per decade of frequency, or 40 dB per decade. And that corresponds to a total phase loss of 180 degrees. So that would mean, in this case, that if I put in a signal, sinusoidal signal like this, then what I would get out would be something that would be, so this would be Vn, say. I would get something that was exactly out of phase. This would be V out. All right, that would be what would happen, for instance, if I put in, this was 1 kiloradians per second. Right, so I'm somewhere up here. At that point, I'm told that my phase is minus 180 degrees, and my magnitude, oh my goodness, my magnitude would be, this keeps going down, I'm going to be at minus 80, minus 120. I will be at minus 120 dB. So if this is 1 here, the magnitude of this guy here is going to be minus 120 dB. If you remember, you get 20 dB per decade, so that's 6 orders of magnitude. So it would have a magnitude of 10 to the minus 6. So if I put in 1 volt times cosine 1000 t, I would get out 1 microvolt cosine, actually I'll have minus because there's a phase inversion, cosine 1000 t. Okay, so this filter has attenuated the signal by 6 orders of magnitude, and in the process there is a phase reversal. There is 180 degrees of phase lag. Now I'm going to stop at this point and pick up on another video, the last video, where we'll talk about second order terms where we have the complex conjugates, complex conjugate roots. But this is sufficient to be able to plot in principle any transfer function of any order, so long as all the poles, that is the roots of the denominator, and all the zeros, all the roots of the numerator, are simple or real valued roots.